Lee Teschler with Machine Design Magazine and EngineeringTV.com. We're here with Peter Hofbauer, the CEO of Ecomotor, and Dave Osberg, a mobility engineer with Tardec. They're here to tell us about a new engine technology.
This is an opposed piston, opposed cylinder engine, and we claim that we can get 4 times the power out of from the same mass. And the reasons are because in this engine the pistons have to travel only half the distance, and the engine speed is limited by piston speed, so the crankshaft runs double the speed. This gives you the first factor of 2 in power density. And second, it's a very sophisticated 2-stroke gas exchange. You can see that the exhaust ports open before the intake port opens, about 30-degree crank angle, and they also close before the intake port close, and that you cannot do in a conventional engine. That you can do only in an opposed piston engine. In addition to that, these rods are always pulling, because after the combustion the piston is driven to the outside, and then the mass forces are pushing it to the outside, and then you have to accelerate again, so it's always pulling. For the same reasons, the inner rods are always pushing. And if you have one pulling, the other one pushing, you have no forces on the main bearings. And so we can have a very light magnesium crankcase, which just have to keep the crankshaft in position. All forces are going to the crankshaft.
So there's one combustion chamber for 2 pistons, that's correct?
Yes. We have one combustion chamber, we have two injectors. It's a diesel engine or JP8 engines for the military. And we have 2 injectors which inject, of course, near top dead center, and it's a conventional diesel combustion system.
Is it difficult to decide on the dimensions of the combustion chamber for a configuration like this?
Well, this is a challenge, and we are still working on it, but up to now we have met all the goals from DARPA. This was originally a DARPA program for the A160 helicopter, and we passed the phase 3 and met all the goals of power density, weight and power, smoke numbers, and also efficiency. But we have to go a long way to make it perfect. So it's not ready for production.
This is a diesel engine. Could it also be a gas engine?
Very easy, of course. This is an easy change. We just need a special ignition system, and we would create a homogeneous mixture, and then we can also run an auto cycle with alcohol or gasoline or whatever.
And how does this compare to a conventional engine of about the same size in fuel efficiency?
Yeah, so we had already demonstrated 220 gram per kilowatt hour, which is about 40% efficiency. But the big advantage is, because this engine is fully balanced, we will have 2 modules, and we can shut off one module. And the downsized version of this in a passenger car would give you an improvement of 40% in fuel consumption, because we can get rid of all the pumping and friction losses of the second module when we run it at partial load, and you run a car most of the time at partial load. This one runs like a 4-cylinder inline engine, and then with 2 modules it runs like an 8-cylinder. But we can run also one module fully balanced, what you cannot do in a 4-cylinder inline engine. It has unbalanced mass for the second order and is jumping. This is absolutely stable on the dyno.
And how do the temperatures and pressures you run into here compare to those of a conventional engine?
Yeah, that's a good question. They're all good questions. There is a high load on the piston grounds, a thermal load. And we have jets, and we jet the oil in an oil gallery, and with that we cool the piston grounds. Cooling the liner is no problem at all. It's just in a short area, and we are cooling the bridges in the exhaust port, so the temperature at the exhaust ports doesn't go over 150 centigrade.
Can you tell us a little bit about the technical challenges you had to overcome to make this practical?
Well, we of course got all the challenges of 2-stroke engines. One challenge is to lubricate the small ends of the pistons, because in a 2-stroke the pin doesn't move from one side to the other. It's always in one direction. You have to get the oil between the pin and the bearing for inner and outer piston. Another challenge is lubricating the piston rings. Yeah, these are more or less the main challenges which are left. But we have solution for this and have demonstrated that.
Can you tell us a little bit about the working engines you've developed using this technology?
Oh yeah, we have demonstrated the working engine which demonstrated the power, the fuel consumption and the smoke number and the weight. Now this engine delivers 300 horsepower and two modules 600, and it's for the truck application. And we will very soon demonstrate it in an FMTV truck for the Army.
And what's the status of your development project at this point?
We have pre-developed this engine, and we are just going ahead with the development. I would guess that we might be able in 18 months to deliver quite mature prototypes to the Army.
So Dave, tell us a little bit about the engine we see here.
This is an opoc engine, two-stroke turbocharged engine. It has potentially benefits for combat vehicle use. Currently, the total system volume under the armor for a combat vehicle is roughly around 3 horsepower per cubic foot. This engine, due to its low heat rejection, small volume and light weight, potentially could lead to a smaller power pack. A power pack includes fuel, cooling system, transmission, air filtration. So your normal two-stroke issues of air consumption, having a large filtration system, could potentially be fixed by this, by having a low air requirement.
And do you envision this as a primary power source or an auxiliary power source?
Currently, the project is to develop a main propulsion engine. There is potential for other applications.
Can you tell us a little bit about the test beds this is going into?
Yes, the U.S. Army paid for this project to be put on a FEV test bed.
Say a little bit about what you're trying to do with this technology.
Well, currently, TARDC is partnering with PMF-TV to do a demonstrator for a tactical vehicle. Further study needs to be done on integrating an entire power pack to see what the entire power pack looks like.
What would you say the major technical challenges?
Well, a major technical challenge to implementing commercial engines in combat vehicles when it's under armor is heat rejection. Fan power becomes very large, and thereby your cooling system becomes very large, and it's a compounding effect with heat rejection. So this style of engine, opposed cylinder engines, typically have lower heat rejection versus a commercial engine.